Hi, my name is Kevin Wilkinghoff. I work at Fraunhofer FKIE, and this short video is a summary about my paper combining multiple distributions based on subcluster AdaCos for anomalous sound detection under domain shifted conditions, which participated in task 2 of this year's DCASE challenge. The organizers of the anomalous sound detection task prepared two different baseline systems, one that uses an autoencoder structure and the other one is based on discriminative embeddings. Here we will only focus on using embeddings for detecting anomalous sounds. I've trained a neural network to discriminate among log-mail spectrograms, more concretely among the different sections that were provided and the different machine types, and also on the attribute information given in the endings of the file names. So yeah, for example, different speeds of the fan. The neural network is based on a ResNet structure and has about 1 million parameters in total. This model is trained using two subcluster AdaCos losses with equal weight. So let's talk about this loss for a short moment. So the standard AdaCos loss is an angular margin loss as arc phase with an adaptive scale parameter, so you don't need to tune any hyperparameters. And the idea of the subcluster AdaCos loss, which has been developed for anomalous sound detection, is to use multiple mean values for each class instead of a single one, and then use a Gaussian mixture model to estimate the distribution of the embeddings for each single class. And then using this GMM, log likelihood value can be calculated to obtain an anomaly score. And this loss yields state-of-the-art performance on the DCASE 2020 anomalous sound detection dataset, and this is the reason why this work focuses on this loss. The major difficulty of this year's anomalous sound detection task was that there were source domains and target domains, and for the source domains there are about 1,000 training samples for each combination of section and machine type, but for the target domain only 3 training samples were available. Since the amount of training data is very different, we use different approaches to calculate anomaly detection scores. So let's start with the source domain. The anomaly score consists of 2 different terms. Both terms are log likelihoods given by a GMM. And one GMM is trained for each section for the machine type, and another GMM is trained for the different attribute information that were given for this machine type. The machine type and the section are known for the test files, but the attribute information is unknown. So we just took the GMM with the largest likelihood for the attribute information and just took the correct GMM for the section. So for the machine type valve, we also added a GMM that is trained just on the temporal maxima of the log-mail spectrograms. And the reason is that this has been shown to yield surprisingly good performance on the DCASE 2020 dataset, and thus, we also thought maybe it also works here. So we trained an additional GMM on this temporal maxima and simply added the negative log likelihood to the anomaly score. So again, for the target domain, there are only 3 training samples. So we have to come up with a way to train something. So we trained 1 GMM for each section and machine type using the data of the source domain. And then we also trained 1 GMM with 3 components for the 3 target samples to have something like a nearest neighbor approach using a GMM. And these scores are combined to calculate the anomaly detection score. Now let's talk about the results we have obtained. We trained a relatively large ensemble, but also only using the model I've described before. And this ensemble consists of 20 subsystems. So the network for extracting the embeddings is trained with different number of subclusters ranging from 1 to 16. And all the networks are trained for 400 epochs, but training is stopped after every 100 epochs, and then the embeddings are calculated and the GMMs are trained and the scores are computed as I described before. This ensemble, consisting of 20 subsystems, is trained a second time, only using a single subcluster AdaCos loss for the sections and machine types. And before, we have used 2 different subcluster AdaCos losses with equal weight. And then the mean of both ensembles is taken, or the best performing ensemble is picked for every machine type on the development set. So, And as a final result, we obtained a system that significantly outperforms both baseline systems and also ranked 3rd among all teams' submissions. Thank you for listening. If you are interested in discussing the results or comparing it with your own approaches, I look forward to see you in the poster sessions. Bye.